SN1 mechanism today, Wednesday. So today we'll look at the arrow pushing of ionization, the reaction coordinate for SN1. And then we'll look at a thing that's unique to SN1 is rearrangement. So an intermediate form than an SN1 is a carbocation. And you have to evaluate whether that intermediate will rearrange. So you have to do it every time, no matter what, and that requires asking some questions about the intermediate. So we'll look at a specific type of mechanism for that. And then Wednesday, when we finish SN1, we're going to look more at the stereochemical issue. So today it's about the mechanism and the rearrangement, and then Wednesday, stereochemistry, and more rearrangements that can happen based on some factors we learned in module 3. Any questions before we get started? Okay, so we introduced this reaction shown with tert-butyl bromide in the presence of ethanol to do a substitution of the bromine to form an ether. And just to recapture some of that detail, we're starting with a tertiary alkyl bromide. And so there's the rate trend for SN1. We don't have to worry about primary or methyl substrates. Again, the secondaries were the gray area that overlapped between SN2 and SN1. So the first key indicator that it's SN1 is the tertiary substrate. The next thing is the solvent, which is also the nucleophile. So it's polar and protic. So you'll notice there's not a strong nucleophile in there. And remember, those are the ionic form with a metal plus and an anion minus. And so the substitution happens where the bromine is now substituted for the O-ethyl. And again, that is coming from solvent, which is also the nucleophile. So one main difference of the SN1 mechanism is the rate limiting step is the ionization of the carbon leaving group bond. So that's going to form a carbon that's positively charged called a carbocation. And then whatever the X group is going to get the negative charge. But the thing about carbocations is that they can rearrange. And so that's a new concept. How does that happen? Why does it happen? So here we see it a little bit more pictorially with structures. And let me highlight with the laser here. First, we'll put in the delta minus, delta plus. It's sort of always important to do that for a polarized covalent bond, because that's showing you how that bond will break. The arrow is pointing towards the delta minus, which means that bromine can accept those two electrons. And then the carbon is going to be positively charged, so that's called a carbocation. And then the bromine's minus. So overall plus, minus, you're neutral. You can never generate an excess of a plus over a minus or a minus over a plus. They always have to balance each other out to give you 0. The other main thing to note, you're starting with an sp3 hybridized carbon. When it ionizes, that's the slow step. So the carbon's now sp2 hybridized. The plus charge is in that p orbital. And see these 3 methyl groups? They all lie in a plane. And then the lobes of the p orbital on either side of that plane. So when the nucleophile, which is the solvent, even though I'm showing it sort of one direction here, so there it's attacking the left lobe, but it also can attack the right lobe. And the reason that matters is because if you're starting with the stereocenter, that's say R or S, when it proceeds through this intermediate and it's attacked, the product stereochemistry is going to be R and S equally. So the center will racemize. So again, how is that different from SN2? SN2, there's always inversion. So with SN1, there's racemization. So as you can see, based on the number of structures here, the nucleophile attacks. You have this oxygen that's plus charged. That's called an oxonium ion. And that sort of resembles something you've seen before. That's called hydronium ion. So that's where the nomenclature comes from. And then a proton transfer to get you your neutral ether. So because we're showing like multiple structures between the starting material and the product, that means the reaction coordinate is going to be a lot more complex than what we've seen for SN2. So here's my my PowerPoint art using the curve tool that's demonstrating that reaction coordinate. And again, the x-axis is your time coordinate. The y-axis is the free energy, so that's the delta G. And then if we're reading left to right, your starting material would be there, and then your product would be to the very right. And so now we're concerned with everything in between. So how many transition states, how many intermediates, and then overall, what is the delta G for the reaction? So how many transition states do you see?
3.
So there's 3. And again, those are the tops or the apex. And then intermediates are how many of those do you see? So there's 2. So I'm going to draw those as sort of this blue well. And then overall for the reaction, you know, we're drawing this horizontal line across. And then relative to where you see the product well, if it's above or below that line, you determine if it's endergonic or exergonic. So overall, we can see that product well is below that line. So I think B is going to be the correct answer. So 3, 2, and exergonic. So those would be, other than the starting material and the product, 3 things that you should be really familiar with interpreting these reaction coordinates. There's usually one of them on the final exam. Let me check something. Okay. The other thing, so there's 3 transition states. And so only one of them will be rate limiting. And so the rate limiting one is the highest one from that line that we drew from the starting material. So that would be transition state 1, transition state 2, and then this little line right there, transition state 3. So just qualitatively looking at it, the energy barrier to transition state 1 is the highest, so that's the rate limiting step. And again, that deals with the kinetics. So with SN1, the ionization step is the slowest. So the 1 means unimolecular, so the concentration of that substrate is the only thing that matters. So here it is now with the transition states filled in, the intermediates filled in, and then some information about the energies required. So as we said, the left-hand side is your starting material. You're going up this hill to a transition state. And so typically in transition states, it's bonds being partially made or partially broken. So that's what you see by the dotted line. That bond is partially ionizing. So that would be the high point. Then it gets to the well, the intermediate, that's the carbocation. And then at that point, again, what you have to sort of envision in your mind is the solvent. And so the solvent is all around this. The bromine could, since it's a negatively charged species, it could attack there and go back that way. But once it falls off, I mean, the molecule is essentially surrounded by ethanol. So the bromine's going to be outnumbered by ethanol, so that's why it attacks. The second transition state is the oxygen-carbon bond partially forming. And then you get into this oxonium ion intermediate. And then its final transition state to the product is that removal of that proton, so a proton transfer. So as we see in the notable notes, only the concentration of the electrophile matters, because that has to ionize to get to the carbocation. So only when that's formed does the nucleophile come into play. The carbocation is sp2 hybridized. We'll understand more of that with the stereochemical aspect on Wednesday, which leads to racemization. Today we're going to focus on the SN1 trend, and really we know it's tertiary is greater than secondary is greater than primary, but in relation to the carbocation, why is that? What are the stabilizing factors for carbocations? And then the complicating factor is carbocations will rearrange. And so it's never a slam dunk. You sort of have to write every mechanism out to determine what the product will be. So in the SN1 reaction, the weak nucleophile attacks which orbital? This is going to be the p orbital. So the carbon's sp2 hybridized, its 1, 2, 3 substituents lie in a plane. And then the p orbital, which is that dumbbell-shaped orbital, the plus charge, again, even though I'm writing it sort of there, it exists in both of those at the same time. So above and below that plane of the 3 substituents is the lobes of the p orbital. The p orbital is a dumbbell shape. And so now with SN1, the 4 identified words here that accurately describe its mechanism. In an SN1 reaction, the electrophile ionizes to a carbocation with sp2 hybridization, resulting in complete racemization of the stereocenter. So that is, I think, D. Any questions? Okay, so what are the factors that affect SN1? So the first one we'll look at is the solvents. So the big difference here is that these are protic solvents, and typically for our purposes in this class, they're going to be alcohols or acids. And the 5 structures that you see, as you progress from left to right, they're ordered in terms of increasing dielectric constant. And one way to think about that is the higher that is, the more it helps break that carbon leaving group bond. It's going to help tug away from that halogen and stabilize the transition state to the carbocation. So acetic acid, ethanol, methanol, formic acid, water. And so not only are these the solvents, but again, they're also the nucleophiles. So they're going to be incorporated into the product. With, maybe we can make a generalization here. So carboxylic acids would give ester products, and alcohols would give ether products. And then if you used water, that would give you an alcohol. So why is there a difference? Why are protic solvents needed? So as we can see through this drawing that's showing hydrogen bonding, so we know that the OH of an alcohol or an acid, the H is delta positive. That heteroatom bromine is delta minus. So there's an electrostatic attraction. And again, what is not very good about the drawing that you see, again, all of these things are space filling. So I'm just showing one solvent molecule. But you can imagine, this bromine is surrounded by all these different solvent molecules. So each little hydrogen bond interaction is tugging on it a little bit, helping the ionization. So the protic solvents will help increase that rate of ionization. The other factor that will affect the rate is carbocation stability. So allylic and benzylic, we've seen what those mean. Just as a refresher. The allylic carbon is the one that's bonded to the sp2 carbon of an alkene. Benzylic is the same thing, except now it's a benzene ring. So those will always sort of take precedence in terms of stability. And then the trend is tertiary is greater than secondary is greater than primary. So the reason that carbocation stability is important is because, again, it's a higher energy intermediate. In anything structurally that can stabilize, it will increase the rate. So in terms of the little lobes, if we have this molecule here, these little lobes right here, those are the p orbitals that make up that double bond. So when the bromine ionizes, that generates this new p orbital where the plus charge resides. And in terms of the resonance, you're now moving the electrons from that pi bond to make a new pi bond, and then the plus charge migrates over to the terminal carbon. So again, keep in mind that resonance really is, it's overall one picture of the molecule informing you where you would see those plus charges. So carbons 1 and 3 of that subunit are going to be have electron deficiency. And so again, this was the benzylic carbon. And if we show that bromine ionizing, now there's a lot more resonance forms because that can be delocalized into the ring a couple different ways. So the more opportunity you get to move that plus charge around, it stabilizes it. And again, that makes it easier to form because it's more stable. Any questions on allylic or benzylic resonance? And so now the next slide is, again, probably conceptually the most abstract, but it does help explain the traditional order of tertiary greater than secondary greater than primary. So two ways of understanding that trend. The first one is through induction. And what we're looking at here in terms of tertiary, secondary, primary methyl, we're looking straight down the axis of the p orbital so that we can see the substituents bonded to the sp2 hybridized carbon. So say, for example, that blue ball is the top of that p orbital. And for this one, we have 1, 2, 3 methyl groups bonded to that. And the red line is indicating that through induction, through that bond, the p orbital is stabilized. The more of those interactions you have, the more stable the carbocation is. So remember, induction is like tug of war through the sigma bond network. And another way of thinking about that, but slightly different, is called hyperconjugation. And so that concept is a little bit more abstract. Now what you can imagine is you put your eyeball right here. You're going to look down this sp3 to sp2, a bond axis. So now you actually see the p orbital. And then of that methyl group, there's 3 hydrogens. And this carbon-hydrogen sigma bond can overlap or align with that p orbital. So the electron density in there is said to be hyperconjugated with that empty p orbital. And the more of those type of interactions you have, the more stable it is. Notice I didn't draw one for methyl because you can't. It doesn't have another carbon there to do that. So this one has a lot, not a lot, and not so many. Way of describing it. So So are we good with understanding this trend? So R plus and so what again, what's going to be complicating about this is you're not only just evaluating that for what you start with, but once you form the carbocation, say you form a secondary carbocation, if it can rearrange to a tertiary, it will. And that can happen two different ways. And so we'll see those over the next 2 days, either a hydride shift or an alkyl shift. And now that's going to coalesce everything we sort of learned in the module 3 about ring strain as well. So remember, like small membered rings are strained and they want to open up. So one way of getting them to open up is through carbocation rearrangements. When I was a graduate student, I TA'd lecture recitations, and this kid came up and said, carbocation, and I was like, what? It's like, anyway. Huh? Carbocation. So we're going to spend the rest of today's lecture looking at a mechanism where a rearrangement does occur, and then how do we spot that? Because once it forms, then there's other questions about, can it go this way or that way, and what's the rational path to choose? So we'll, where do I have it here? Okay, I have it right here. We're going to use this alpha beta nomenclature. So the carbon bearing the leaving group we're going to call alpha. And then every carbon bonded to that we're going to call beta. And so they don't necessarily have to be the same type of beta carbon, so they all can be different. And therefore we have to evaluate each path individually to see if a rearrangement can occur. So the rearrangements can happen two ways. Now that says hydride. It doesn't say hydrogen. So hydride is, again, that. And then methyl or alkyl, that's CH3. Or a ring. A strained ring can open up. When we show that stuff, the arrow might look a little bit weird in how things shift. But always keep in mind that when a shift happens, the plus charge is migrating from one carbon to the carbon right next door. And so the take-home message is that this only works one way. You can only form a more stable carbocation. If you start with a tertiary, it's not going to downgrade to a secondary, and it's for the most part, you're never going to get sort of lateral rearrangements as well. And that will become a little bit more clear when we look at these mechanisms. So without further ado, this is the reaction. So we're starting with a secondary alcohol. Hydroxyl is a bad leaving group. So it just doesn't leave as OH minus. That really never happens. However, under acidic conditions, so we see that with hydronium, and then we're in the presence of methanol. You can get that OH group to eventually leave, and then it's substituted now for CH3O. So you're forming an ether. When you look at the reaction as it's drawn, does something stand out to you? Like just visually looking at what you're starting with, what you're ending up with. So the OH is on carbon 2, and then in the product, the O-methyl is on carbon 3. Everything we've seen so far is the substitution is occurring at the carbon bearing the leaving group. But here it's not. So notice that carbon 2 has OH and then H. This carbon 2 has 2 H's. This carbon 3 has a hydrogen, but now it does not. So if we put all of that together, that's going to help explain mechanistically what's happening in this rearrangement. So let's go ahead and start drawing some things out. What's reasonable to do here? What's reasonable to account for? So again, I'm going to say the carbon bearing the OH, that's the alpha carbon. I've just numbered the chain in blue according to the nomenclature rules. That's what that is, so that we can keep track of hydrogens, oxygens, that sort of thing. So a secondary alcohol. We're treating that with hydronium, H3O plus. So the reasonable thing to do, if hydronium's an acid, the alcohol acts as a base. So it gets protonated. And so now that's the oxonium ion. Now we can break that carbon-oxygen bond, because when we do that, water is going to be the neutral molecule that leaves. So we formed a secondary carbocation. I've labeled, that carbon alpha. And then when we look at what's bonded to it, there's a beta carbon, and then there's beta prime. So methyl is beta. This one over here, that's beta prime. on the beta carbon, there's 3 hydrogens. If we have one of those hydrogens shift, what class of carbocation will that form? It's primary. So when I draw this shift, as I've sort of darkened there, those electrons in that CH bond are moving over. So that's hydride, H minus. And then the plus charge is going to where that H was. So now for beta prime, if that H migrates over, what class of carbocation do you end up with? So this H right here is going to migrate over. So now you end up with tertiary. So secondary to tertiary is allowed. Secondary to primary is not allowed. And if you think of it in terms of the reaction coordinate, if you're at secondary, primary would be higher in energy. So nature does not want to go higher in energy. When tertiary is lower, it can go there easier. And so that explains why that carbon gets 2 hydrogens. Then the methanol will come in. To attack. So you end up with that oxonium. It undergoes an acid-base transfer to get the neutral product. So the sort of take-home message of this is anytime you form a carbocation, you always have to look at the attached beta carbons and see if a rearrangement is going to occur. So this was called a hydride 1,2 hydride shift. On Wednesday, we'll look at other types of shifts, so methyl or alkyl. Methyl is sort of the same thing. Instead of H, you have CH3 moving over. An alkyl shift is typically when you want to reduce ring strain. Rings can open up. So a 3-membered ring can become a 4-membered ring, 4 to 5, that sort of thing. And this is, this stuff really happens. I mean, it was proven through labeling experiments of steroid work back in the 50s and 60s. So it is important. Any questions before we get to some more questions? So these remaining questions are just meant to walk us through that step by step so we understand exactly what's happening and how we diagnose moving forward. So upon protonation of the hydroxyl group at carbon 2, the C2 oxygen bond ionizes to form what type of carbocation? So we have a secondary alcohol, and so when that ionizes, it's going to form a secondary carbocation. And really that is sort of the blinking red light to indicate to us we have to look out for rearrangements. If you form a tertiary carbocation to begin with, chances are you're not going to have to worry about rearrangements. So how many unique type of beta carbons are there? Again, I say unique because if there's not symmetry, they're going to be different, and they can form different carbocations should a rearrangement occur. So there's beta and then beta prime, so that's going to get you 2. And again, my advice is to always evaluate each of those independently so that you're confident in how you're disproving one over the other. So in terms of their class, again, this can also help you figure out where to go. This is primary. This one is tertiary. So that answer would be B. And that's going to help you determine how the rearrangement happens if it's going to happen. So we're starting with secondary. Again, the choice was this. So yes, it will rearrange from secondary to tertiary. I think that's all I'll say about that without maybe let me redraw this. So one thing that may be confusing. So see that plus charge? Always keep in mind, we're not showing implicit hydrogens, but that does have a hydrogen. So that may be a better representation for you, so you're not losing track of the H's. And so that H, again, migrates over. So now we can see those 2 H's, and then that carbon becomes positively charged, so it's tertiary. Again, my advice as well, I'll put it in here, 1, 2, 3, 4, 5. That blue numbering is the numbering of the chain for the nomenclature. That can help you as well. Again, if an answer is cheaping you out on the number of carbons or it's adding too many, knowing your total carbon count can help you eliminate some derailer answers. And finally, the last one, you're forming that tertiary carbocation. It's trapped by methanol. And it says, does the final product have a stereogenic center, yes or no? I saw an emphatic yes, and then I saw the counterpoint no, so it does not. It might look like it just by how sort of weirdly it's drawn. So again, that's getting trapped. So it's getting trapped by OCH3, and the reason it's not is because you have ethyl and ethyl both bonded to that carbon. So don't let this bond rotation fool you into thinking that it's a stereogenic center when it's not. That's, I guess, the last slide today. Any questions? So now Wednesday, again, is going to focus on the stereochemical issue. If you start with a stereocenter, you ionize it. What happens if rearrangements occur that then get trapped? How does the stereochemical information flow through that mechanism? And so we'll look at a couple more of these shifts as well, primarily methyl and alkyl shifts.